Hello everyone. This lecture is exclusively made for second year BSc student of BK College Kalyan of physics and maths combination. So we have already uploaded few lectures on Riemann integration. Today I will prove one more properties of Riemann integration, that is if f is R integrable function on closed interval a comma b, then the modulus of a function is also R integrable. So let me write down. This lecture is exclusively made for BK Birla College Kalyan students. So my result is as follows. If f is R integrable on closed interval a comma b, then mod f is R integrable. So proof. So it's given that f is Riemann integrable on close interval a comma b. So if it is R integrable, means it will satisfy the Riemann criteria. So by Riemann's criterion, for every epsilon greater than 0, there exists a partition P of close interval a comma b such that UPF minus LPF is less than epsilon. This is number 1. Let capital P is equal to x naught, which is a comma x1 comma x2 comma dot 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 xn, which is equal to b, be any partition of close interval a comma b. So instead of saying be any partition, I'll say be a partition of a comma b. Right, now define capital Mi, which is equal to supremum of fx such that x belongs to xi minus 1 comma xi, then small mi is infimum of fx such that x belongs to xi minus 1 comma xi. My capital Mi dash is equal to supremum of modulus of fx such that x belongs to xi minus 1 comma xi, and small mi dash is infimum of mod fx such that x belongs to xi minus 1 comma xi. Right. I have to prove that UPF is mod f is R integrable. So that means mod f satisfies the Riemann criteria. So if I could prove that for the same partition P, UP mod f minus LP mod f. If it is less than epsilon, then we can say that it is mod f is R integrable. So this property number one, or the number one, will help us to prove this. So let's write down. So first we will prove that capital Mi dash minus small mi dash, that supremum of mod fx and infimum of mod fx, is definitely less than equal to capital Mi minus small mi. From graph also you can visualize, but those who do not visualize through graph, we can prove this. Now you may wonder why I'm doing this. So soon it will be clear, because if I prove this, then my 99% task gets over. So this will help us to prove the mod f is R integrable. Okay, so let me prove this. Basically, this is my this is my claim. So let me prove this. So since uh, capital Mi is a supremum, small mi is a infimum, then that would imply f of x is lying between small mi to capital Mi for any x belongs to xi minus 1 comma xi. Similarly, f of y lie between mi to capital Mi for any y belongs to xi minus 1 comma xi. So let's write down that. So we have f of x lies between small mi to capital Mi, and hope it is clear with a capital Mi. So let me write down in a capital Mi, and small f of y is less than equal to again capital Mi to small mi. This is true for any x comma y belongs to xi minus 1 comma xi. So if I take any point between x and y, they are point from the subinterval xi minus 1 comma xi. So if I take any point, then definitely f of x and f of y will lies between capital Mi and small mi. Right. So what I'll do, I'll multiply this particular inequality by cap minus 1. So what I will get is as follows. So this would imply Mi less than equal to fx less than equal to capital Mi, and now second inequality I will multiply with minus. So capital Mi will come this side. Now the inequality, when we multiply by minus, then the sign changes. So you can see that previously I had small mi less than equal to f of y less than equal to capital Mi. When I multiply with minus sign, then minus mi is greater than equal to minus f of y, which is greater than equal to capital Mi. So writing that greater than is same as I have just wrote in a less than form. So capital Mi is less than equal to minus f of y less than equal to, because you got, if you realize this, you got this like this mi greater than, because when I multiply by minus sign, this everything changes, symbols changes, because you can see that if I multiply this with minus sign, I'll have this. Writing this is basically this only. So I am not written this now. So I'll read, because they means one and the same. So why I did this minus? So I wanted to add these two inequalities. So if I add these two inequalities, let's see what I'll get. So add this and this. So if I add this, what I'll get is as follows. Small mi minus capital Mi is less than equal to f of x minus f of y less than equal to capital Mi minus small mi. That would imply if I take minus sign common, then it will be capital Mi minus small mi less than equal to f of x minus f of y less than equal to capital Mi minus small mi. Now you could see that f of x minus f of y lie between minus mi, capital Mi minus small mi, minus and plus. So we have a result. If x lies between minus a to plus a, that means mod x is always less than equal to a. So that property I will use. So in fact, you know this property. It's a nice property of real number. So if x lies between minus a to plus a, this if and only if mod x is less than equal to a. Right, so maybe I do not have a much space to complete that, but I'm sure that you all will understand what I mean. So that would imply modulus of f of x minus f of y lie between capital Mi minus small mi. So that would imply modulus of f of x minus f of y is less than equal to capital Mi minus small mi. Now this would imply mod of f of x minus mod of f of y is less than equal to mod of f of x minus f of y, which is less than equal to capital Mi minus small mi. We had this property, if you remember, mod a minus mod b is always less than equal to mod of a minus b. So this property I'm using. So mod f of x minus f of y is definitely greater than mod fx minus mod fy. So I'm interested in first and third in part. So that I will write it now. So this would imply modulus of f of x minus modulus of f of y less than equal to capital Mi minus small mi. So maybe I will repeat this in next slide also. So this would imply what I got is that f of x mod of f of x minus mod of f of y is less than equal to capital Mi minus small mi. Right, for all x comma y belongs to xi minus 1 comma xi. Now this would imply, let me write down, mod fx is less than equal to mod fy plus capital Mi minus small mi. Now what I will do, fixing, now I will fix y here. So if I fix y, then f of y will be constant. So if this is constant, capital Mi is constant, minus Mi is also constant. So entire thing will be constant. So mod f of x will be less than equal to a constant. That means that constant is going to be upper bound for mod f of x. But we are already knowing about one of the upper bound of mod fx, that is Mi dash, which is a supremum. So this is a upper bound. Mi dash is also upper bound for fx, but that's a supremum. So that would imply my supremum must be less than equal to any upper bound of that function. So I will have capital Mi dash less than equal to mod f of y plus capital Mi minus small mi. So let me write down that, things will be cleared soon. Fixing y from xi minus 1 comma xi, this would imply f of y will be fixed. If I fix y, then f of y will be fixed. So this would imply modulus of f of y plus Mi minus small mi is upper bound of mod fx. उसके लिए वो अपर बाउंड हो जाएगा. But we know already one of the upper bound of mod fx. But mi dash is least upper bound of mod fx. So I got one upper bound as mi dash and another upper bound as mod f of y plus mi minus capital small mi. So this would imply mi dash must be less than equal to mod f of y plus capital Mi minus small mi. This would imply capital Mi dash minus capital Mi plus small mi less than equal to modulus of f of y. Now what I did, I fixed the y. Now I will release that. So if I release the y, then this f of y will be now variable. So this would imply, so I now here I have released the y. That's very important. So this is true for all. Now how I say that I have released, so now I am saying that for all y belongs to xi minus 1 comma xi. That means y is a variable now. When I say here for all y, that means it got released. Now for all y, my modulus of f of y is always greater than equal to this. That means it is going to be a lower bound for modulus of f of y. So this would imply capital Mi dash minus capital Mi plus small mi is lower bound for mod fx or fy also you can say, but that x and y are dummy variable here. So is a lower bound for mod f of y. You can say f of y, not an issue. वहाँ पे कुछ difference नहीं होगा. If it is lower bound, but we already know one of the lower bound of f, mod f, but small mi dash is greatest lower bound of mod f. Instead I'm writing mod f of x or mod f of y, I'm straight away saying now mod f. That is fine. So this would imply mi dash is a lower bound, और ये कैपिटल mi dash माइनस कैपिटल mi प्लस स्मॉल mi ये भी लोअर बाउंड है, बट स्मॉल mi dash is the greatest lower bound. So what I'll get, mi dash minus capital Mi plus small mi is definitely less than equal to small mi dash. Right. So what I'll do now, so small mi dash minus small mi, capital Mi dash minus small mi dash is less than equal to capital Mi minus small mi. So this is what I required. If you remember, somewhere I have written. First we will do, so which completes the proof part. Now what I'll do, I'll multiply this by xi minus 1, and then I will take the summation over it. So what it will give me, summation I goes from 1 to n. This is capital Mi xi minus 1 minus summation I goes from 1 to n, small capital Mi dash, small mi dash xi minus 1, which is less than equal to, here also I will have same, summation I goes from 1 to n. Actually I wanted to write down separately, but now since I have a late space, so I will write down here straight away, capital Mi minus small mi into xi minus 1. What I did, I wanted to repeat on this expression. First I have multiplied. So see, I have written very 2-3 steps I have clubbed it. But while writing in a paper, how one should write? After this, one should say multiply the above inequality by xi minus 1. Then you multiply throughout the expression. Then next line, take summation over the above expression. Then when you will take the summation, you will have this expression. Now you can see this. This is my mi dash is a supremum of mod f. Small mi dash is a supremum of mod f. So this is up mod f, upper sum of mod f. This is upper sum of lower sum of mod f. And capital Mi is a supremum of f. And minus small mi is a infimum of f. So this is upper sum minus lower sum of small f. What I got is as follows: up mod f minus lp mod f is less than equal to upf minus lpf, because you can see that right hand side is mod f का रिमनन क्राइटेरिया बन रहा है और लेफ्ट हैंड साइड mod f का बन रहा है एक्सप्रेशन, राइट हैंड साइड में f का बन रहा है, बट दिस इज ऑलरेडी लेस देन एप्सिलॉन फ्रॉम 1. So by Riemann criteria, we can say that mod f is R integrable. Now next question is the converse of this statement is true? Is converse true? Answer to this, no. Converse is not true. That is, if mod f is R integrable, that does not imply f is R integrable. If this is not true, I should give a counter example where mod f is R integrable but f is not R integrable. Then it will be more clear. So counter example. A best counter example is your Dirichlet function. F of x is equal to 1 minus 1. X belongs to rational, x belongs to irrational from close interval 0, 1. So f is not R integrable. That we know. I don't want to express that. But mod fx is 1 here, which is constant function, and constant function which is constant, and we know that every constant function is R integrable. So mod f is R integrable but f is not R integrable. So you can see that mod f is R integrable, that does not imply f is R integrable. So here f is not R integrable. Fine. So this completes a very nice property of Riemann integration. So in upcoming lectures we will even prove few more properties of real number, not real number, real valued function I will say. So in upcoming lectures we will prove a few more properties of real valued function. Thank you so much.